Hello everyone and welcome back to this online NPTEL course on aquatic geochemistry. In our previous lecture, we had been discussing about the basics of stable isotope geochemistry, and in this lecture as well we are going to deal with the basic fundamental processes that leads to stable isotope fractionation, especially in aquatic systems. So, as we have already discussed a lot about equilibrium in our first few lectures. So, equilibrium processes and the thermodynamic properties of the molecules, they themselves can include some isotopic fractionation. And whenever there is a kind of exchange reaction is happening, there can be sometimes preferences for either the lighter isotope or the heavier isotope depending on the energy of the system. Okay. So, it is a difference in the thermodynamic properties of molecules with the different isotopes that exert this kind of equilibrium isotope fractionation. So, that means in an equilibrium process, this exchange is continuously happening and it is at a steady state. Okay. It is at equilibrium. Okay. So, the isotope exchange reactions get get exchanged continuously and it is at equilibrium. Okay. So, for instance, if I am using this exchange reaction of oxygen isotopes, that is getting exchanged with carbon dioxide and water. Just imagine two huge reservoirs. Okay, water is an extremely huge reservoir and carbon dioxide, which is there in the atmosphere as gaseous form or dissolved in the water. Both of them have huge reservoirs, and here the possibility of equilibrium reactions are more. Okay, because of its continuous nature, always they are exchanging. They are just exchanging the atoms. Okay. And here the common atom is that of oxygen. So, either they are exchanging the heavier oxygen or the lighter oxygen, but always the molecule which has the highest bond strength will incorporate the element with the heavier isotope. Okay. But this exchange is going on. Okay. So, if you compare carbon dioxide and water, the bond strength of carbon and oxygen as compared to hydrogen and oxygen is far more in carbon and oxygen. So, the carbon oxygen bond strength is very good, very high. So, therefore, 18 oxygen always prefers CO2 over H2O. So, 18 oxygen will be preferred in carbon dioxide as compared to water. Therefore, that kind of fractionation is happening. Okay. Now, the equilibrium constant of the reaction, if I am going to write of this particular reaction, then it is just the left terms or the product terms divided by the right hand terms, that is my reactants. Okay. Or if we are going to write in terms of isotopes, we are going to write the 18 oxygen by 16 oxygen of carbon dioxide by the 18 oxygen divided by the 16 oxygen of water. So, this is the gainer of the heavier isotope and this is the loser of the stable isotope. So, this is the equilibrium processes, that is continuous exchange reactions that are happening, and this is not related to any kind of added energy. Okay, it is just happening in nature continuously always. Now, let us look into a few mathematical terms, therefore, the notations that we will be using henceforth. And one of the extremely important notation is this alpha term. This alpha is the isotopic fractionation factor. Okay, it is called the isotopic fractionation factor between these two phases. So, isotope is fractionated between two phases. For instance, 18 oxygen got fractionated between carbon dioxide and water. So, those are my two phases A and B. Okay. So, alpha fractionation between two phases A and B will be the ratio in the phase A divided by the ratio in phase B. Okay. For instance, we just looked into this example. So, this is exactly how it is. So, alpha of CO2 and water is the delta 18O by 16 oxygen in my CO2 divided by 18 oxygen by 16 oxygen in my H2O. This is the fractionation factor, how it is written. Okay. And R is the always the ratio of the heavier isotope to the lighter isotope, and that we are going to report in parts per mil. Okay, it is going to be reported in parts per mil, because you see in the previous lecture I showed you that the differences are happening in the third, fourth, fifth decimal places. So, we write them in parts per thousand. Okay. A positive value, okay, if this difference, if this delta value that we are going to write, if a positive value is there, that means the ratio of the heavy to lighter isotope is higher in the sample than it is in the standard. So, this is what the delta notation stands for. The delta notation stands for the ratio in the sample, that is my x, minus the ratio in the standard. For instance, the standard can be SMO, VPDB, air. Okay. So, these are the standard reference materials that I am going to use. So, that standard entirely divided by again that standard into 1000. For instance, if I am using 18 oxygen, if I am trying to find out, I am going to write the isotope ratio 18 by 16 oxygen of the sample minus the 18 oxygen by 16 oxygen of the standard minus 1 into 1000. And this is how we are going to report, that is in parts per mil, that is parts per 1000, and our standards for 18 oxygen can be VSPO, it can be GISP, GISP is Greenland precipitation, or it can be VPDP if I am measuring delta 18 of carbonates. So, using those kind of reference materials we are going to measure, and this measurement is directly done on the isotope ratio mass spectrometer. It is a specific instrument that is used to determine stable isotopes. Okay. Let us see some more facts that comes out with these values. So, a sample with a delta 18O value of plus 19.7 parts per mil has this oxygen isotope ratio, that is 18 oxygen by 16 oxygen isotope ratio, that is 19.7 parts per mil, or in terms of percentage I will say 1.97% higher than that of the standard. Okay. So, with respect to the standard, it is 1.97% higher. Okay. And this differences between two substances, that is substance A, substance B, they can be using this isotope ratio mass spectrometer, they can be detected at a very low level, such that even differences in the 8th decimal degree can also be measured. Okay. So, it can be an extremely low number also can now be, with technological advancements we can also have started to able to measure that. Now, let us see what is the relationship between the isotope fractionation factor and the delta notation. Okay. So, if the alpha term, if I am having the isotope fractionation factor term between 2 A minus B, that is equal to 1 plus, if I am writing in terms of delta. So, delta A divided by 1000 divided by 1 plus delta B or the other phase divided by 1000, which is equal to 1000. If I am just trying to write the equation. So, 1000 plus delta A divided by 1000 plus delta B. Okay. So, if I am having a phase, so for instance there is a liquid phase and a vapor phase, then it is 1000 plus delta in L divided by 1000 plus delta value in the vapor phase. So, it is just the composition in the vapor phase and the composition in the liquid phase. Okay. What is that value? So, the fractionation factor, if I am trying to find out, for instance, if I say delta L liquid value of 18 oxygen is minus 10 parts per mil, okay, and the delta V, okay, delta V is equal to minus 20 parts per mil. Find out what is the fractionation factor, find out what is the alpha value. So, the alpha value of 2 L by V is equal to 1000 plus delta L, that is for me it is minus 10. So, I will write minus 10. So, here this will change to minus 10 and this will be 1000 minus 20, that is for the vapor phase. So, here I will have 990 and here I will have 980. So, it will be something around 1 point something value. So, that is the fractionation factor, that is the isotopic fractionation factor value. Another notation is in this term, that is the del. Okay. So, del of A minus B is equal to delta A minus delta of phase B, and that if I now write in terms of alpha fractionation factor, that is equal to 1000 times logarithmic ln natural log of alpha in this A minus B, the fractionation factor for A B phase. Okay. And if this if we are going to do some more approximations, then we can write alpha minus 1 into 1000 for this change, the delta A minus B. Okay. So, the delta A minus B is just the difference in the delta values. For instance, if I write what is the delta value of LV, that is minus 10 minus of minus 20, right, that is minus of minus 20, that is 10 parts per mil, that is 10 parts per mil. So, that is the delta notation, that is the del notation. Okay. Now, how are we going to write this isotope fractionation factor term in terms of the equilibrium constant value? So, alpha in terms of equilibrium constant value is also could be written into alpha is equal to the equilibrium constant value to the power of 1 by n, where n is the number of atoms that is getting exchanged. Okay. So, k is this term, right. So, this is also equal to alpha in terms of this equation, because here n is equal to 1. It is only one atom that is getting exchanged. So, therefore, in this equation where 18 oxygen is getting exchanged between carbon dioxide and water, the equilibrium constant value is equal to the isotope fractionation factor. Okay. So, the values of alpha are very close to unity. They will be generally typically be 1.00 something value. Now, whenever we are writing the thermodynamic equilibrium constant value, that is K. Therefore, and we are equating it with alpha value, we always have to measure the temperature, because this equilibrium constant is a function of temperature. So, this alpha values are meaningful only if the temperature at which it is measured is specified. Okay. So, whenever we get these alpha values, we always have to note down, okay, at what temperature is it. So, alpha of carbon dioxide and water is equal to 0.004120, 1.004120 at 25 degrees Celsius. Okay. So, that means that the delta 18O, if I am working with water isotopes, stable water isotopes, that is delta 18O, okay, then carbon dioxide is 4.2 parts per mil heavier than the water with which it has equilibrated, because these are all equilibrium reactions, right. So, the water with which it has equilibrium, carbon dioxide is 4.1.2 parts per mil heavier. And how do I did this calculation? Simply this 1.00 rule. Using this simple 1.00 rule, I know this is my alpha value. Okay. So, this simplification is just that this is equal to x. So, if my alpha value is 1.00360, then 1000 times log of alpha, that is equal to the difference between the two phases, is 3.60, 3.60 parts per mil. Okay. Now, let us see some values of the hydrosphere. So, we are going to talk about all the aquatic systems, right. We are going to see the aquatic system and how stable water isotopes specifically is applied in the aquatic. So, now we are going to move into the hydrosphere. Okay. Now, stable water isotopes of hydrogen and oxygen are conservative traces. What do I mean by conservative traces? That means they are going to get mixed and they are going to remain in that in the water body with respect to the sources. Okay. So, the delta 18O of a mixed reservoir will be the delta 18O of source A, okay, plus the delta 18O of the source B. So, this is what I called conservative mixing, that if I am seeing at a mixed value, then this I know has come conservative, it stays stable from the mixing of these two end members. So, this is what I mean by conservative traces, that they do not get changed with chemical processes, but rather a lot of physical processes, more of physical processes as compared to chemical processes. Okay. Now, chemical processes also affect, exchange reactions are also happening, but they are mostly equilibrium reactions. But what is at non-equilibrium is the physical processes. Okay. So, evaporation, condensation, these are the more reactions which is at non-equilibrium. So, therefore, these kind of physical processes is going to fractionate these isotopes, and therefore, we are going to see a huge variations in the different kind of reservoirs. For instance, ocean, the delta D value is 0 plus minus 5. Now, it is not exactly 0, but we assume that it is at 0. We consider the oceans 0 value, we have given that value as 0. For instance, when we are measuring a particular mass, we have assigned a certain mass a value. For instance, we have taken this much amount of a certain substance and say, okay, this substance of this much amount is going to be said to be 1 kg at this particular temperature. Okay. So, such kind of approximations has to be done. So, when we are going to measure something, we are going to say, okay, my ocean is my reference for everything else on earth. That is my largest reservoir of liquid water on the planet, and in fact of the entire water on the planet, and that is in the most being the largest reservoir, I am going to say that that particular reservoir is 0 value. So, it is 0 and it can have plus minus values of 5 relative to the different locations. So, there is a lot of spatial variability. So, that value can change. So, 0 plus minus 5, and for oxygen isotopes that is 0 plus minus 1, and this is with reference to this particular standard called SMO. So, SMO itself is the ocean water, right. SMO itself is the ocean water. So, when I am going to measure ocean against ocean, its value comes to 0, right. Here as you see, I am using the standard. Now, here if I am measuring ocean with ocean, so this is also ocean and this is also ocean. So, if I am subtracting ocean minus ocean, the value comes to 0. So, therefore, this is 0 plus minus 5 depending on the spatial variability, and this has a little less variability 0 plus minus 1. Then there can be other different ocean masses. So, there is a deep Atlantic ocean mass, there is a deep Pacific ocean mass, there is a deep Antarctic ocean mass, whose 18 oxygen compositions are different. Okay. They may have the similar kind of delta D values, that is 0 plus minus 5, but here it is more of plus 0.005 or minus 0.15 or minus 0.40. The ice caps and the glaciers, which has the next largest volume in terms of mass, the volume coverage on earth 2.15% of water, that has the most negative delta D value and the negative delta 18O value as well. But it has a huge range, look, minus 230 plus minus 120. So, huge variation in as we go to the more colder regions. Okay. Same for delta D and for 18 oxygen also, there is a huge minus 30 plus minus 15. So, basically it can vary between minus 45 to minus 15, that variations is there for ice caps and glaciers. Groundwater 0.62 percentage in volume on earth varies from minus 50 plus minus 60, that is pretty negative, and also minus 8 plus minus 7. So, just a little bit heavier than the ocean water. Fresh surface water, that means rivers, lakes, accounting to 0.017 volume, that again has a huge variability minus 50 to plus minus 60 to minus 8 plus minus 7. So, very little positive, more of the negative side variations. Atmospheric water, okay. Atmospheric water is the vapor, water vapor in atmosphere, minus 150 plus minus 80, so mostly negative, and minus 20 plus minus 10. So, again huge variation in terms of delta D, comparatively lesser variation in terms of 18 oxygen. Let us see the natural isotopologues of water, how the different water molecules have the variations in their isotope molecules and the way it is arranged, the geometry. So, H216O if I am trying to find out what is the abundance, okay, I am going to see that the hydrogen isotope with protium, that is 1 hydrogen H, has a very high of course abundance. So, that is 0.999 abundance, and the same 16 oxygen, that also has very high abundance. So, water having both the atoms with the lighter isotopes has the highest abundance. So, water with both the hydrogen and the oxygen with the lighter isotopes will be the maximum possibility. If I now exchange one hydrogen atom with the deuterium, so one protium gets exchanged with deuterium, then I will have I will multiply the abundance of hydrogen with the abundance of oxygen or deuterium now, and also again with the isotopic abundance of the 16 oxygen. So, this is the total abundance of a molecule having one protium and one deuterium on earth. So, that means that H2 comprises 99.6% of all water on earth, while HD is hydrogen and deuterium, 16O, that combination comprises of 0.03 percentage of all water on earth. That is just due to the differentiation of the isotope abundances. But note that 0.03 percentage of all water. Now, water has a huge volume on earth. So, even that is very precisely able to measure it. We are going to able to measure such small differences also very precisely using the current technological advancements. So, we can have a lot of different isotopes of water starting from H2 then there can be one HD or it can be HD118 oxygen or with 17 oxygen. So, there can be different permutations and combinations in which this isotopes can be arranged, and similarly this is their isotopic abundance. Therefore, you see the abundance of a molecule with both very heavy isotopes, that is 18 oxygen and both atoms of hydrogen with deuterium, has the lowest abundance. That has the lowest abundance. So, these are the natural isotope abundance of oxygen, and this is the natural abundance of hydrogen. Okay. So, this is the probable forms of a molecule of water having one hydrogen and one deuterium and 116 oxygen, and that is how the symmetry looks like. So, it is just different ways that the bonding can get changed. Now, another extremely important process that causes fractionation of stable water isotopes and very relevant to understanding of aquatic systems is the Rayleigh fractionation, and this fractionation happens during the evaporation and condensation processes. Okay. Let me just explain to you this figure. In this figure you will see there is a ocean, okay, there is a ocean, and this is the continent. Okay. This is the continental outline. Okay, this is the continental outline. In this x axis you will note there are latitudes plotted. There are latitudes plotted. So, this is the equator, this is the tropics, more higher latitudes, and there the pole. Okay. Now, ocean is here close to the equator, and this ocean has the delta H value of 0 parts per mil. Okay. Now, when evaporation is happening, when these oceans, when evaporation is happening in the ocean, as we have seen due to kinetic processes, that the lighter isotopes will get more preferentially evaporated as compared to the heavier isotopes. So, in this vapor, the 18 oxygen will be low in number as compared to the 16 oxygen. So, there will be more 16 oxygen and lower 18 oxygen. Okay, it will be more 16 oxygen and lower 18 oxygen. Now, when this evaporation process is going on, if there is any condensation that is happening, if there is any precipitation event that is happening, okay, 90% of all precipitation events happen in the oceans itself. Only 10% of the clouds move onto the continents. We just receive 10% of the global, all the evaporation of the precipitation events, we just receive 10% of it. 90% of these precipitation events happen on the ocean itself. Now, when this precipitation is happening, the 18 oxygen prefers the more stable phase, that is the liquid phase, as compared to the gas phase. As we have already discussed, the heavier isotope always prefers the more heavy, more stable phase as compared to the more lighter and non-stable phase. So, the 18 oxygen, whatever was there in the cloud, will preferentially go to the precipitation, that is a rain, as compared to the vapor. So, all my 18 oxygen now gets more into the rain. So, the rain value has a value of 18 oxygen of 0 parts per mil. That is, it is more 18 oxygen enriched as compared to 16 oxygen. Therefore, when this cloud is now moving from position A to position B, the 18 oxygen in the cloud is further lowered, because the 18 oxygen is already gone into the rain. So, the remnant vapor has got even lower 18 oxygen. So, the cloud now has a 18 oxygen composition of minus 25 parts per mil. But when that rainfall is happening at this position B, when this position rainfall is happening, again the rain will have preferentially more 18 oxygen as compared to 16 oxygen. So, whatever now 18 oxygen is left in the vapor, again that will preferably go towards the rain phase. So, the rain will be isotopically heavier as compared to the vapor. So, the rain has minus 15 parts per mil value now, while the cloud gets more and more depleted. So, this cloud, which is now again going farther interior of the continent, more and more towards the higher latitudes. Now, at this position C, the 18 oxygen composition of this cloud is now minus 40 parts per mil, that it is continuously losing the 18 oxygen to the rainfall events. So, it is getting more and more depleted, more and more lower in the 18 oxygen concentration. So, its value is minus 40 parts per mil now. Again, any rainfall that is happening at this particular location C, if the rainfall is happening, rainfall or snowfall, whatever is happening, that rainfall or snowfall has got whatever is the remnant 18 oxygen. So, again the 18 oxygen is going to preferentially be more in the rain as compared to the vapor phase. So, now the rain has a value of minus 30 parts per mil. So, just note the changes of how the cloud composition is evolving, of how the rain composition is evolving. So, the cloud is gradually going negative and the rain is also gradually going negative, but the most enriched reservoir is my ocean, most stable liquid phase. From here starts these isotope fractionation processes of evaporation, where it first got differentiated, but rain it collected all the 18 oxygen. So, it had a value of 0 parts per mil again, similar to the ocean. With subsequent rainfall, the rainfall is getting gradually more and more negative composition. So, here it is minus 25 parts per mil. As it is going towards the more interiors, it is getting more negative. Now, let us see another final position D, which is very close to the poles. Here the cloud now has become extremely depleted in terms of the heavier isotope, that is 18 oxygen, and there is more of just 16 oxygen left. And when that rainfall is happening, or basically it is snowfall that is happening, that is forming the glacier, the ice, it is getting compacted, solidified to form ice mass. This ice mass now has having this very negative value, minus 60 parts per mil. So, across the latitudes you see the variation. So, more towards the equator, more positive values, lesser fractionation between the heavier and the lighter isotopes. With subsequent rainfall events, more and more 18 oxygen gets preferred in the rainfall, less and less 18 oxygen remains in the remnant vapor phases. As these vapors moved more towards the inland and goes towards the pole, they become gradually more and more depleted with 18 oxygen, and the last place, that is near to the poles, where the all precipitation gets completed, the entire is changed to snowfall. There we receive very the snowfall is rich in 16 oxygen, but very low in 18 oxygen. So, the ice composition, the snow composition, or even if it is rainfall in the form of rain, these values will be extremely negative, very high negative values as compared to the values that we saw in the close to the tropics, close to the continental coastal lines. Okay. So, this kind of fractionation is called Rayleigh fractionation. Okay. So, therefore, when you see these values of SLAP, okay, this is some kind of Antarctic precipitation, light Antarctic precipitation. So, this light Antarctic precipitation has a value of minus 55 parts per mil of delta 18O. So, now you understand why from Vismo to the glaciers, why the delta delta 18O value of ocean is more positive, or 0 value, while the ice caps has a value of minus 30 plus minus 15, right. It is due to this Rayleigh fractionation factor. So, with this I will stop in this today's lecture, and I will continue discussing about this more in the next lecture. Thank you.